Well, good afternoon, and thank you to everyone at Hello Tomorrow for making it possible for us to be here in person and to talk about the future of sustainable aviation. I'm going to start with a small bet. I'm going to bet that I'm the luckiest aerospace engineer that you're going to meet today. And that's because I'm working with a talented group of people with a purpose to rethink the skies. We're working to grow the contribution, the economic and well-being contribution that aviation can make in the less well-served parts of our market. We're also working to unlock some of the constraints that we see around us in the busiest parts of our transportation networks. And most importantly of all, we're working to do this while reducing the emissions footprint of aviation. That's just an imperative for us. And it's something that we've been working on for quite some time. So my journey to get here to Paris yesterday was an absolute delight. It was fantastic. I came on the Eurostar. I walked into the station in London, into St Pancras, showed my passport, showed my ticket, went through the metal detector, walked up and onto the platform and boarded the train. And I got here in comfort, quiet surroundings. I was able to work, I was able to eat a nice meal. And of course, when I got here, I walked off the train, down the platform and straight out into central Paris. My alternative would have been to book a flight. I'd have had to go out to the airport, check in at the terminal, get through security, find my gate, wait, get on board, hope I got an aisle seat so I could move around a little bit on the flight, and then do the really fast middle bit, airport to airport. And then repeat the exercise at the other end to get off the airplane, through the airport, back onto the train and into central Paris. That would have taken me 2 hours longer to take the plane rather than the train. It would also have multiplied my carbon footprint of that journey by a factor of 10 times more. So valuing my time and valuing my carbon footprint, as I do, I hope you understand why I chose the train. But the only reason I could do that was the legacy of big infrastructure projects that we have around us in this part of the world. You know, the TGV here in France, these low emissions energy sources that power that, the Channel Tunnel itself, the high-speed rail links in the UK. And almost nowhere else on Earth does that apply. Nowhere else on Earth, almost, could I have overcome the geographical boundary between the two countries that's formed by the sea so easily. And if my choice had instead been about taking a ferry or taking a flight, it wouldn't have been such an easy one to make. Let me give you an example. If we wanted to travel from Barcelona to Mallorca, city centre to city centre, Barcelona to Palma, that's just over a 4-hour trip on the flight, but it's nearly 10 hours if we go by boat. So now our decision's harder. Do I trade 6 hours of my time to cut my carbon emission footprint of the journey by a factor of 10, or do I just take the flight? And of course, that's the choice that we're faced with in transport and logistics in much of the world today. Now, the reason that some of those travel choices are so binary comes down to some physics. And I'll try and illustrate it here with a very simple chart, perhaps better thought of as a 4-box model rather than a graph. And on here, I've charted the size of the different transportation systems that we have, their maximum payload, set against the energy that they use when they're doing their journeys, which of course is a function of their payload, yes, but also of their speed and of the distance that they can travel. And what we find is that we have two broad groups of options that sit on this chart. The first here are aircraft, things that have to expend energy just to keep themselves aloft and expend energy to carry their payload and also expend energy to carry the fuel that they use and also move forward to get to their destination. And these aircraft, they travel fast. That's a great benefit of air travel, but it's also a requirement. If we're going to carry all that weight in the air, we need to be moving fast to do it. Around the rest of the chart, we have the things that we use to move around on the surface, roads, railways, and shipping. Now, these options, very efficient, but can't usually travel as the crow flies. And they need infrastructure, often lots of it, roads, rail networks, ports. And so we've got a set of things that fly fast and a set of things that need infrastructure and a gap between those. Now, that gap between them was first defined by two researchers back in the 1950s, Theodore von Karman and Giuseppe Gabrielli. And they wrote a paper called What Price Speed, and they mapped all this out much more rigorously than I have done here. And what they determined was that there's an intermediate speed range in which this gap occurs. The speed range between the aeroplane speeds and between the typical ground transport speeds, that's an area where we've not been able to define or produce a system that is as efficient as those other options on the surface or in the air. So we have an efficiency gap here defined by intermediate speeds. And that has some real-world consequences. It means that we're flying aeroplanes, for example, on short sectors because the next best option is so much slower, which is leading to emissions that we could theoretically avoid. It also means, there are cargoes moving around the world that would be quite okay if they arrived at their destination in a couple of days, rather than the couple of the hours that the airplane gets them there in. But they couldn't sit in that journey for 6 weeks, which is what it might take traveling by sea. Unless, obviously, it means that we're condemning parts of the world to be underdeveloped because we need big infrastructure projects if we're going to develop those out. And when we have infrastructure in place, it also means once that infrastructure gets saturated, it's expensive and difficult to expand it. So we don't often notice those consequences, but they're all around us. So what we're doing in hybrid air vehicles, we have an aircraft called Airlander. And Airlander is designed to operate in that intermediate speed range efficiently. And the way it does it is it lifts some of its weight for free using buoyancy. So some of our weight of that aeroplane is offset by buoyancy. So we're not lifting the whole thing, not expending energy to keep the whole thing in the air. We then add fuel and payload, and we generate the extra lift needed to lift that by moving the whole aircraft through the air, and it operates like a lifting body, a wing, and generates the rest of the lift we need. So much more efficient because we get that head start of buoyant lift. It's also designed to operate without major infrastructure. So it operates off any reasonably flat, large surface, be that grass, ice, marsh, tarmac, can even be water. So we're really looking to take that efficient center ground and open up our opportunities to get that deployed into parts of the world that aren't well served by infrastructure right now. And that, of course, allows us to grow services in places that aren't well served right now. It allows us to provide an extra flexible capacity around congested and vulnerable networks that we see around us today. And it allows us to avoid the unnecessary emissions that are caused if we try and squeeze those other transport options to address things that can be addressed in that intermediate speed range. Now, the big challenge for every industry is decarbonisation, and aerospace is certainly no exception to that. In fact, because aircraft have to carry the fuel that they burn, we need particularly energy-dense fuels in aerospace. Kerosene has fit that bill right from the start. And now we need to move away from it. And there's a lot of work, and a lot of it evident in this building this week going on. At bottom left of this scale, we've got air taxis, and batteries will indeed allow us to have small aircraft carrying small payloads for relatively short distances. But we've got a problem scaling battery technology up. It would take batteries 30 times more energy dense than today's just to be able to carry half the number of passengers, 1/5 the range of our current single-aisle aircraft. So the industry is also looking hard at hydrogen. Hydrogen looks very promising. And again, a lot about that around us here today. But it's going to take some time. We're going to need to design the accommodation of a different fuel onto aircraft. We're going to design those, certify them before they can go into service. And it's also going to take time to scale hydrogen up into our fleets. Consensus seems to be that we'll start to see hydrogen aircraft in significant numbers maybe by the middle of the next decade. They may never make it to the longest range aircraft. And so here, sustainable aviation fuel's extremely important, whether as a stopgap or whether as a long-term solution. The ability to use biofuels or synthetic fuels to power big aircraft is likely to be an important part of our future. But we have a scale-up challenge there. We need land resources, we need energy, we need green hydrogen in the synthesis, and all of those resources are also in demand from other sectors. So when I look at that picture from an aerospace point of view, I feel slightly humbled by the challenge that we've got, and I think it becomes important for us all to understand that we've got a set of engineering steps to go through to decarbonize aviation. We don't know what the full end state of that looks like yet. And because we're moving away from kerosene, which has been the one fuel that the industry's used right from the start, it's likely that we're going to see changes in the physics of the aircraft that we see flying as we change the physics of the fuel that we're using. So then when I look at a rounded landscape like that, I do see opportunities. I see opportunities for quick wins. I see those opportunities now that we have something coming into the market which is closer in speed to the aircraft, to start to move away from using those fast aircraft on really short sectors. I see opportunities to connect the air system into shipping in different ways. Airlander's designed to directly carry shipping containers, so connecting from the sea to inland in less developed parts of the world suddenly becomes possible without big infrastructure projects. And I also see some integration going on here. You know, can you envisage journeys that perhaps start with a railway trip, transfer onto an Airlander as we get into an area of the world with a geographical boundary, and maybe the last part of your trip is distributed out in the final miles through air taxis to your final destination. So there's some ways that we can integrate across these different services, to these different systems, to get to lower carbon services more quickly. So near-term quick wins, the ability to put the right energy into the right system, a view that we may not stay with a one-size-fits-all approach as we move aviation away from the kerosene it's depended on for so long, and the ability to scale up some of our battery and some of our hydrogen technologies into aircraft that operate in a slightly different way and use that energy effectively in an intermediate speed range. Let me draw all that together for you in just one of our use cases for Airlander. I'm going to go back to the example I started with. So this is what your journey on an Airlander might look like. This would look like affordable, fast and direct 100-seat air travel, but in a journey that feels a little bit more like the train ride that I enjoyed yesterday, where there's space, there's the ability to move around, there's the ability to work, it's a quiet cabin. Your journey might not start or end from today's airports, because we're breaking that link away from needing the heavy infrastructure to operate the aircraft. And during your journey, you can relax, look out the windows, and enjoy that spacious and accessible cabin. Practically, your decision now is a little bit different. Instead of looking at the difference between a 4-hour trip and a 10-hour trip, you're looking at the difference between just over 4 hours and 4.5 hours. So now the choice is, do I take 20 minutes longer on my trip to cut my carbon footprint of that journey by a factor of 10? And my second bet of the day is I'm not the only person in the room that would choose to do the right thing there and cut the carbon footprint at the expense of a 20-minute addition to my day. The other thing I'd say about this picture is I think generally, as we face up to the challenges that we've got in this decade, the innovations that we're going to need are a mixture of incremental innovation and disruptive innovation. And what we have here is something that's more disruptive. It's different. It doesn't necessarily fit our preconceptions of how we move around the world. But that's the point of a disruptive innovation. We won't always see those coming. And when it comes to aerospace, I think that brings me back to the point that to overcome the challenge that we've got to deliver the great services that we're all used to and to expand those in parts of the world that haven't had the benefit of those yet, we're going to be looking at a range of solutions here and no one size fits all for the future of aviation. So there's challenge, there's also a lot of excitement as we bring these new technologies through. And coming closer to home, in our business, we're bringing to that market a flight-proven, ultra-low emissions aircraft that's unconstrained by infrastructure. It starts with a 10-ton payload, or the 100 passengers, with 50 and 200-ton versions planned to move up and into the broader logistics market. And although I've mostly talked about transport and mobility here, core to the way that we've designed the aircraft is to have one aircraft capable of fulfilling many roles. So mobility on the one hand, logistics roles, and also using the efficiency of the aircraft to be able to fly for very long periods of time and provide surveillance capability, protecting people and protecting things on the ground. So it's my hope that in the last 15 or 16 minutes, I've got across to you that at least when it comes to aircraft, faster isn't always better. Also that I think we're going to see a range of solutions and see a broader spectrum, a broader palette of options available to us as we move ourselves around the world in the future. And I hope that in some small way, I've helped you rethink the skies just a little bit. Thank you very much.
Hello, Tom. All right. Where are you going to try this out? I mean, you were mentioning, trying to get through geographical borders where it might be also more feasible than really going from, let's say, Paris to London or whatever. So where do you try to launch this?
Yeah, well, as you saw, the aircraft, and as I said, we've been working at this for a while. The aircraft's flown. We've developed the technology, and it's exactly about, as you say, now deploying it into the first parts of its market. And that will start in some of the less well-served areas of the world, and it'll actually start with some tourism applications. So you saw the space and the comfort that you can be in there. So if you imagine being able to do an air safari or an air trip into a remote part of the world, that part of our market has really got on board with this very, very quickly. So I think that's where we'll see some of the initial proving happen. But the interesting thing for us is that the last 2 years has meant that the next stage of this has come forward much more quickly. We've seen this great unfreezing of our attitudes around what it means to travel and what it means to have harmful emissions as we travel. And so the regional aircraft market is now seeing its business model be threatened by that. And so I think we're going to see Airlander come into those markets much sooner than we originally thought.
Mm. And do you think also education plays a part? Because a lot of the people that were here on stage said that if the customers are basically educated and you have also a good communication strategy, that people will push into these new areas to really get these projects off the ground as well?
There's no doubt. I think we set out to develop a platform thinking that we had some technology challenges ahead of us. But I think with hindsight, the biggest challenges have been about communications. It's been about communicating what it is, where it fits, why it's important, what it can unlock, what benefits it can bring. And so we brought that thinking about communications into the heart of how we operate as a business, because as I think other speakers have said, you have familiarity problems with new technologies, and you also have chicken and egg problems. Without the customer moving, the capital markets, the financial markets don't move, and vice versa.
Mm. And we have already some questions also from the floor, and probably because a lot of people saw the shapes, so it reminds them of something old school. So what gas are you using? Is it flammable? And also, how is Airlander different to old school Zeppelins or blimps? You get that question quite a bit.
I've had that question once or twice, yeah. So first things first, we're now in 2021, and so the technology we deploy is different in every way to the technologies that people will have seen in those prior generations of airships. So I think the simple answer to that is all of the materials, all of the elements of it, and including the gas that's inside are obviously designed for 21st century requirements and with 21st century technologies involved. Now that leads you to question, well, is it the same as an airship? And if so, why haven't airships worked up till now? Well, for us, it's really very different from an airship, and the difference is that we do not create, Airlander doesn't create all of its lift from floating. It doesn't float. It sits on the ground when it's not flying, like other aircraft do. And economically, and that's because we've got that combination of lifting forces that I talked about earlier. And practically, that's really important from an economic standpoint. Anybody who operates any asset, let alone an aircraft, will tell you that it makes its money when it's in the air. And having an airship floating on a mast is not an easy way to turn it around for its next flight. It's not easy to fuel it, defuel it, get passengers or cargo on and off. So the whole ethos of the company and the whole design of the aircraft has been about getting almost lighter than air, almost that airship efficiency, into something that actually, to the operator, operates much more like the normal aeroplanes that we see going in and out of their fleets on a regular basis.
And some people in the audience are also wondering, this seems to be a very old concept. Why hasn't it been implemented largely so far?
So again, the airship concept is a very old concept. Our design moves us as much to fixed wing lift and as much to that gap between aircraft and surface transport that I talked about, as much as it pulls anything from the airship world. And the answer to the question, why hasn't it happened before, is back to that economic point. We can have very, very efficient flight using airships, but that doesn't equate to very low through-life operating costs. It doesn't equate to the things that actually have our airline customers making money, and it's been solving that problem through the package of technologies, including the overall platform, which we've designed and patented within the company, that is key to the way that we're working this market.
And I think some people also would like to try to use your Airlander, because somebody's already asking, with a larger service area, how well does it cope with turbulence and strong winds? So somebody already wants to book.
Well, that's one of the really nice things about traveling in Airlander is the vibration that you'll feel in the cabin, the noise that you hear in the cabin. We have to put cameras for our pilots to see that the engines are running because it's so quiet inside that cabin. And its response to turbulence is really quite nice and benign as well. So none of that fast bouncing around that we're used to when we're sat in our airline seat with the seatbelt strapped up.
Also going to be on a different, let's say, altitude?
Different altitude and a beautiful view. So I don't know if you were able to see in that picture I put there, you've got floor-to-ceiling windows. We even put some windows in the floor so you can look through if you want to. And that will be a fantastic way to experience the world as you pass over it at a few thousand feet, 4,000 feet, up to 10,000 feet, whereas our airliners are really up in that 30,000 foot sort of height.
All right. Thank you so much for taking up to this altitude today. Thank you so much.
Thank you.
Thank you, Tom.